Okay, so today we are going to talk about behavioral synthesis. This topic is also referred to as high-level synthesis in the literature. Basically the idea is that synthesis refers to the process of transforming a functionality of a design into a structure. The structure consists of the components and their interconnections. So in case of behavioral synthesis, we start from a behavior or an algorithmic description, and the reason it was called high-level synthesis was to differentiate it from logic synthesis. In case of logic synthesis, we start from Boolean equations and generate a netlist of gates which can realize the Boolean equations. In case of high-level synthesis or behavioral synthesis, we start from a behavior which is specified not in terms of the Boolean equations but in terms of a more abstract level. And so primarily the requirement comes from the fact that there is urgent need for pushing up the abstraction level, at which the design can start. Why do we need to push the abstraction level? It's just to handle the complexity. See, when you are doing designs which has 50 transistors, you can go down and design at the transistor level. When the number of transistors in a design goes up to few thousand, you cannot go down and design at the transistor level, but you go up and design at the gate level. But still you are handling few hundred gates. But when your complexity increases to thousands of gates, you cannot design at the gate level. Then you design it at the RTL level, where you look at adders, multiplexers, decoders. But even once that complexity also increases to hundreds, which is today the case when we have hundreds of RTL components, then it's no longer possible to design at the RTL level. Then we need to go up the level, and at that level we have to also start describing. So instead of doing a structural description, we are also going to design with behavior. So once the complexity increases, is the only way to reduce the design turnaround time. Interestingly, what had happened is, though the complexity is increasing, but the product lifetime is decreasing. The product that is released in the market today typically lasts for 2 to 2.5 years. Within 2 to 2.5 years, it becomes obsolete because of the changes in technology, the speed, performance, the user requirements, and so on. So because of that reason, the product lost in the maybe it has a good demand for a year, year and a half, and then another year you can market it, and beyond 2.5 years the product dies. And so what is the type of a design turnaround time you can expect for a product which is only going to be sold for 2.5 years? It should not be more than 6-7 months. You cannot talk in terms of a design cycle turnaround time which is more than 6 months or so, because otherwise the product is not going to be successful. So there is a pressure to reduce the design turnaround. And how do I reduce the design turnaround? The only way you can do it by increasing the productivity, and the way you can increase the productivity is you can raise the abstraction level of the design. You don't go down and design at the lower levels, but start designing at the higher levels. So that's one of the reasons why behavioral synthesis is becoming popular, so that you can write a description at a higher level. And this is also a very interesting reason that an algorithmic description of the functionality is far easier to write than designing hardware. As a stream, let's say if you want us, let's say it's like differentiating between teaching design and teaching programming. Programming is far easier to teach because in terms of stepwise assignment, in terms of algorithmic description, a human being is far easily trained to be able to describe what he needs, the functionality that he needs in terms of the steps to break it down. But in terms of trying to teach someone how to design hardware is far more complex. So what one really need to do is, if you can actually push up the design to the behavior level, where the functionality is just described by the algorithm, and the lower level nitty-gritties of timing as well as the hardware details are really kept out from the designer, a lot more people can become designers, or at least participate in the design process at some level. It's also far more economical to employ people who understand programming than to, even in terms of numbers. So that's also one of the reasons. And the second thing is, as VLSI is getting introduced in all walks of life, like basically, let's say you're talking of a car manufacturer, he's also going to have some ASICs as part of his cars in future cars. Even now cars contain processors and so on. Similarly, almost in any other, so a person who is an automobile engineer, he very well knows what the functionality that he requires from this chip. What are the things that he needs to control, the fuel injection and so on and so forth, measurement of various parameters. But he or she is not going to understand how the hardware is designed. So if you can actually go up and start the synthesis process from the behavior level, even an automobile engineer can design, theoretically at least, can design the product that he requires without going to a hardware designer to do. At least one can write the description which can be taken as a specification by a hardware designer and can be worked at. Otherwise, the specification that is worked at by a hardware designer would be completely inconsistent with what is required, because there is always going to be a very ambiguous means of communication in terms of what is required. And so algorithmic descriptions are easier to write, faster to write, and also the complexity increases. So these two are driving the design into higher levels of abstraction, and behavior synthesis is one of them. In the next class we will also talk about system synthesis issues, but today we are going to talk about behavior synthesis, which is given an algorithm, given a procedure which performs a computation, a specific computation, how do I generate a hardware which will meet that computation? We already did this process manually in case of the GCD. When we looked at the VHDL description and when we looked at the GCD design, even when we described the state machine, we started from a GCD description and tried to synthesize a state machine for it. So today we are going to just generalize that and try to talk in terms of what are the steps that are involved in performing such a behavior synthesis. There are very complex algorithmic issues which are involved in it, because once you want to automate this process, and there are a lot of graph algorithms and a lot of other algorithms that are employed in terms of a lot of optimization that is employed for doing this. And of course, those of you who later on do the CAD course will study some of them in more detail. Right now I will describe the steps and also give you an indication of what are the type of things that are required to be done at each of these steps. We already discussed this in this course in quite a length, that we talk in terms of data path and control and how they interact and so on. So this is something which we have focused right through the course. So the design techniques that are employed for data paths are different from the design techniques that are employed for control. Primarily because the data path typically does all the computations, all the data transformations, and you require modules which are fairly complex and you don't want to go down and design these modules each time in terms of the basic gates. I need an ALU, or I need a memory unit, I need a comparator. So if I want to build a 32-bit ALU or a 32-bit comparator starting from gates, it's going to require a large number of gates. So it's not advisable to each time go down and design something down to the gate level in the data path, because the complexity of such circuits, the modules, is very large. Similarly, if you want a memory which is, let's say, 8 kilobytes memory, you are not going to design. So these are typically done either pre-designed, these cells are available, these modules are available, and the data path is designed in terms of these modules, and I will talk about how it is done. Whereas in case of the control, it's different. Control is very specific for each design. Once you write an algorithmic description, you require a certain control flow to carry out that algorithm. What is basically an algorithm? Algorithm is nothing but a sequence of steps that you need to carry out to meet the functionality. And what are each of these steps? Each of these steps are basically some arithmetic operations, some logic operations, some conditional testing. As long as there is a sequential flow, I can transform such an algorithmic description into something like a state machine, where I assign at each state what are the steps that need to be carried out, what operations need to be carried out, what conditions need to be tested, and based on that, what is the next step that is to be carried out. So that is how the control synthesis is done. You take an algorithm and convert it into state machine or some form of representation which is equivalent of that, and then synthesize the state machine. We already know how to synthesize the state machine. We have manually done it, but also automatically also we know how to synthesize the state machine. You have to do the state assignment, and then you have to do the next state synthesis of the logic for the next state. And once you have done your state assignment, you already have your Boolean equations, and you can go ahead and we will talk about that. So this is the process is at the first step itself is split into these two. You identify the operations that need to be carried out by the data path, and then you perform a data path synthesis, then you generate the state machine and do the control synthesis, and finally you do the clock synthesis. But the data path synthesis process itself is not simple, and it requires a lot of steps, intermediate steps, and we talk about them also in some detail. There is a first thing that we need to do is scheduling. We will talk about this. Resource allocation. Resources here refer to resources for performing data transformations. What are the resources for performing data transformations? These are functional units. Addition, subtraction, comparison, all these things are functional units which are referred to as one of the resources. Resources for storing data. The resources that are needed for storing data are registers, register files, memories, so on and so forth. So that you require to have registers for that. Buses for transferring data from one place to another. So buses and interconnects, of course, there could be point-to-point interconnects, there could be buses. Buses are shared for transferring number of data. From number of data sources, you can take the data out on a bus. They have to be disjoint. Interconnects are, on the other hand, point-to-point interconnects. They are only used for transferring data from one source to one destination. So allocation process refers to how many of these units, what type of units and how many of these units I need to allocate. That is the one process. Then I need to do the binding. The binding process is the next process where I actually specify which operation will be performed on which functional unit. I will again talk about a little more detail. So these are the three primary steps that are involved in data path synthesis. Though I have written them in this order, but we will see that there is a lot of influence. The reason this problem is very complex is there is a lot of correlation between these two. When you do scheduling, you also are actually constraining the resource allocation space, or vice versa. When you do resource allocation, you are also constraining the scheduling space. I talk in terms of the space, which is essentially the design space. Okay, we talked of the area time before. So basically the design space refers to the point, a design point which has a certain performance, certain area. It could also have a certain power consumption. Power is also important. So each one of them they have a strong influence on the other, and so they cannot really be performed independently, or you have to do it interactively, or you have to do it, best is you have to do it in an integrated manner. But each of these problems is complex enough, and integrating them makes it even more complex. So typically what is done is some decisions are taken, sometimes even with some user inputs, and then some decisions are taken using tools. But a lot of tools have been developed in the last 10 to 15 years and is becoming available commercially now. So let's look at the problem of scheduling. Okay. So problem of scheduling is assigning operations to control steps. When we say control steps, finally I will map a control step to a clock period. But I need to assign operations to control steps, and as I said before, this phase has a lot of influence on resource allocation, because if I say that I have two operations, let us say I have two operations, V1 is V2 plus V3, and then I have another operation, let us say V4 is V5 minus V6, two simple operations. Now in my scheduling I have to take a decision that in some control step, let us say in control step S, whether I do these two concurrently or not. Whether I am able to schedule them together or not in a control step depends upon number of things. One of the things it depends upon is whether I have one adder and one subtractor available to me so that I can actually perform these operations together. So I cannot schedule them together. So if I schedule them together, I will force, if I am going to do my resource allocation later on, if I do my resource allocation after I have done scheduling, if I schedule them together, I will force that there should be two units at least. There could be two ALUs, of course, both are capable of performing both addition and subtraction, but minimum there should be two units, one capable of performing addition, another capable of performing subtraction, because I want them to be scheduled in the same control step. So what this shows is the resource allocation and scheduling are very closely coupled. Okay. So when you are talking of an algorithmic description, one is starting from a description of this nature. So now, though of course this particular statement looks trivial, and if I need to map it on, so I need to map it on to hardware, I can say that okay, I have one register, I have another register, I have another register. This stores V1, let us say this is register R1, this is R2, this is R3. This stores V1 and I connect it like this, and I can now control it. From my control I can give an enable in this particular control step S corresponding to S, and then I can perform this operation and store the result. But this type of a design decision is only one method of implementing this. After all, you don't want to have registers for each of the variables. There could be hundreds of variables in your description, and you don't want to have hundreds of registers in your design. So this particular simple control step, which is simple operation, which is V1 is V2 plus V3, you might like to convert it into memory read into some register. So you are reading a memory. So what you are doing is, and now let's say the same memory is storing V2 and same memory. So you have two operations now which are memory read operations, and then you have an addition operation. So this is your read operation, this is your read operation there. You might like to convert this into this. And you may have a data path which is, let us say there are two registers, and from this memory, which is some memory, and then this is, let's say, R1, R2, then you bring the data over here, and then you perform the addition, bring this into some register R3, and then you put it back into the memory. So you may have a memory write. This is one type of a design that you are mapping onto this. This is another type of a, here you are not doing anything but just putting these variables into the register. So now, as we will see later on, that this process of where these variables reside is going to be decided at the binding stage. And whether I need a memory or not for implementing my design is also to be decided at the allocation stage, the resource allocation stage. But at the scheduling stage, if I am allocating a memory and I am storing these values in the memory, at the scheduling stage I have to reserve a control step for reading. So this is for reading V2, memory read V2, memory read V3. So I have to assign a control step for doing each of these read operations. So this is the problem that one faces over here, that we talked in terms of these three phases that are involved in doing a data path synthesis. One is scheduling, which is assigning operations to control step. One is resource allocation. Another is binding. But you can see that all these three are coupled together. You cannot do these three things independently, because translation of the same statement could result in just doing an add operation, just one particular node which is an add node, or it could also result in this type of a, you read from memory and then perform an add and then perform a write. So you could have, so your scheduling could be, you may need to have control steps for doing each one of these. So that is what I refer to here. This phase has a lot of influence on resource allocation, as what can be done concurrently depends upon the resource availability. And why does the complexity arise? Complexity arises due to the range of available functional units. I will talk about this range when I am talking of the resource allocation problem, but we will see that, because even when you say that addition is to be performed, your library could consist of a very large type number of modules which are capable of performing addition. If you have only one type of an adder available in your library, then the problem is simpler. Any addition will map onto that. But you could have various types of units, and these units could differ from in their capability, that is performance. You could have a ripple carry adder and you could have a carry lookup adder. Both are available in the library, and the tool which is actually synthesizing would have to make a decision which one to use. Okay. Similarly, you could have pipeline multipliers. Multipliers where there is a 4-stage pipeline and you can actually get a throughput of one multiplication every clock cycle, but the latency is 4 clock cycles. And the latency and throughput, so when you talk of something which is pipeline, let's say a multiplier which is it's a pipeline multiplier, and I can feed in, so there are 4 stages over here, I can feed in a input every clock cycle. So I will get an output every clock cycle, but I will get the first output after only 4 clock cycles. So now whether I use this or I use something which has a larger delay, the throughput is going to be reduced, but the latency is also less. If I have to choose between these two multipliers, so this decision has to be done. It's not easy because latency also affects the performance, because an operation which is dependent upon this multiplication result cannot start for 4 clock cycles. It's not just the throughput. So, but if there is an application where, let's say, I have to do a multiplication of 2 arrays, this may be a good solution. You are, let's say, taking a dot product. If you are taking a dot product, what you are doing? You are actually performing something like xi, yi over I. You are doing something like this. So then you can start one multiplication. All these x's and y's are available in parallel, and so you can start pushing one set of operands each clock cycle, and you can do this fairly fast. But for some other applications where this is not the requirement, something else you have to do, so this may not be a suitable solution. You may be better off having a multiplier which actually takes, so this may be working at 100 megahertz, that means 10 nanoseconds for every multiplication, but something which works at only, let us say, 40 megahertz may be preferable, though it takes 25 nanoseconds as the delay, but its throughput is more, less. It's only 40 megahertz, but its latency is also less. The result is available after 25 nanoseconds. Here the result is only available after 40 nanoseconds. Though you get, so, but if you can utilize this multiplier very well, you can feed the values continuously, this may be a preferable solution. So these are some of the complexities that come when I want to, a manual designer has to analyze and do it, but a tool also has to analyze and do it, and that analysis can become fairly complex. Let's talk of the resource allocation problem, and I will also talk about, so typically resource allocation is done manually, at least the major resources are allocated manually. Some of the interconnects could be synthesized automatically, but automatic allocation algorithms are also getting available now. So primarily when you talk of the FU allocation problem, which is a more complex problem where you try to design how many functional units, complexity due to range of operators. This is what I had mentioned in the scheduling also, and let me explain to you. So I already talked about the pipeline. Multifunction, you all know, ALUs are multifunction units. Operators which can perform not just one function, but it can perform multiple functions are multifunction units. Multi-cycle, when you allow for a particular operator to not to take just one clock cycle, but multiple clock cycles, then they are called multi-cycle operators. So, okay, so here the issue is complex because of the fact that the clock period is not decided a priori. You only know the delays. How many clock cycles you will allocate for performing when you are doing your scheduling. You have a multiplier which takes, say, 25 nanoseconds. You have a multiplier which takes 25 nanoseconds, and you have an adder which takes, let's say, 10 nanoseconds. These are, let's say, the major delay units. Now how do I decide? So I have a choice of doing two things. I can either say that my clock period is governed by this. So I have 10 nanoseconds and my multiplier will take 3 clock periods to perform a multiplication. If I do that in a synchronous design, I am wasting 5 nanoseconds for doing my multiplication, because after all it will take 30 nanoseconds to do the multiplication. I am adding up all the setup time, hold time is all added up here. Assume that these are including that. So I have a choice. I can either choose a clock period which is 25 nanoseconds and perform this in 1 clock, and I can take 1 clock for doing this. I will be wasting 15 nanoseconds for performing an addition operation, because I will be latching the result only after 25 nanoseconds. So it's like taking 25 nanoseconds for the adder, though the addition takes only 10 nanoseconds. Or I can choose a clock period which is 10 nanoseconds and allow 3 clock periods to do the multiplication. Both these solutions have advantages and disadvantages. It all depends upon the situation. Whether wasting 5 nanoseconds on multiplication is less desirable than wasting 15 nanoseconds for the addition, depending on how many additions are being performed, how many multiplications are performed, which of the operations are present in the critical path, and so on and so forth. So even this decision is going to be, so now I have in the library I have, what will I have? I will have a library consisting of my components, and I have a component which is stored, which is multiplier, which is 25 nanosecond delay. I have to make a decision whether to use this, as a component which takes 3 clock periods, or I have to use it as a component which just takes 1 clock period. Because my scheduling is going to be affected by this. I have to assign at which control step I am going to feed the inputs to it and which control step I am going to feed the outputs from it. So these type of operations are called multi-cycle operations, and the design becomes more complex because of this. Mixed speed operators. As I mentioned to you, multiplication can be done using number of, you can have multipliers which are very fast. You can have Wallace tree, carry save adder. There are many multiplications. Just like in case of addition, you can do it ripple carry, carry look ahead. Similarly, in multiplication, of course, consists of number of additions, so there are even more choices over there. So first of all, the issue is if you have the different speed operators, which operators to pick up is a decision that the tool has to make. Not only that, when it is doing allocation, it can also pick up, for example, 2 multipliers in the same design, one fast multiplier and one slow multiplier, and map the operations depending upon their criticality either to the fast or to the slow multiplier. If the operation is very critical in terms of the being present in the critical path, it may perform it in the fast multiplier. So all those decisions also have, make the complexity of the design process more. So that is as far as the FU allocations goes. Then we talk about the storage allocation. Storage, you have variety of storage units. So primarily we talk in terms of registers and memory ports. But increasingly, when you talk of memory units, you just don't talk of single port memories, you also have multi-port memories. What does multi-port memories mean? We have a memory unit which can perform, let us say, there are 3 address sources, read A, address read A, address read B, address write C. So I have 2 outputs and 1 input. This is port A, port B, port C, and this is a 3 port memory. What this memory is capable of performing, of course there will be other signals which are required. So what will this be able to performing is in the same memory cycle, it can read 2 locations and it can write into 1 location. You can have 1 port memory, 2 port memory, 3 port memory, and also the functionality, whether how many read ports, how many write ports, whether there are some bidirectional ports, and the number of varieties that are available in the memory, and they all have an influence in terms of the performance that you can get, because after all typically every operation requires 2 operands and you generate a result. So if you can do all of them in 1 cycle in a memory, then you can do things faster if you have to go and get the data from the memory. So the resource allocation phase has to take care of what size memory, how many memories, and how many ports for the memories and so on. Register files are similar to memories, but except that they are set of registers, and so they are present, so they are not typically a separate unit, they are present as part of the design, and they are, so you can have 8 registers, 16 registers, 12 registers as part of a register file. And the access is similar to, you access the memory, you access it through the addresses, and you access these registers, and again you can have register files which can access more than 1 register at a time. You can access 2 registers or 3 registers at one time. So these are all related to allocation. We have to decide which type of units to allocate and also how many to allocate, because after all I can decide to allocate 2 slow multipliers rather than 1 fast multiplier, and I may save in terms of I may get a better performance because I can push in 2 multiplications simultaneously. So the allocation problem is what and how many, what to allocate and how many to allocate. From the library, so you are given a library of components and you have to choose. So this is the selection phase, and if a tool has to intelligently choose it, so it has to look at the algorithm, it has to look at the requirements of the algorithm, and it also has to look at the performance that is required from the implementation. Now let us come to the resource binding phase. This is the third phase, scheduling I said, resource allocation, resource binding. Not necessarily done in this order. Sometimes resource allocation is done first, then scheduling is done. Sometimes done in an integrated manner. Resource binding what is the binding that needs to be carried out? We need to bind operations to operators. When I say that, you may have the example that we took. So I may have this particular operation. Let's say I need to perform this, and I may have one adder, and I may also have one ALU. In the binding phase, I need to decide whether this addition should be performed here or it should be performed here. So mapping the operations to the operators, once I have allocated both this and this, I have more than one possibility of performing this operation. I may have more units actually. If I have a lot of concurrency, I have a lot of very high performance unit, I may have multiple such operators available. And the process of binding refers to which operator that I need to, or which functional unit I am going to use to perform the operation. So that is one type of binding. The other type of binding is variable to storage unit binding. Variable to storage unit binding. So I have some registers. Let's say I have 4 registers. I need to decide V1 should be bound to, let's say, register R1, V2 should be bound to register R4, V3 should be bound to register R2. So I have to make this decision. This is called the variable to operator binding. If you look at it, this is the phase where it starts looking like a compiler. This phase of the synthesis process somewhat resembles a compiler, but basically this is a much more complex than the compiler because of the following reasons. A compiler typically has a fixed architecture. If you consider a processor, you all studied the MIPS processor. A compiler for MIPS would know that how many registers the MIPS has. Whereas here, this is a variable part. It is not a fixed architecture, it is an architecture which is getting designed, synthesized for each application. So I have to have a very general type of a compiler. So this is the phase where I am trying to decide which variable is going to reside in which register. So this is a problem which every compiler has to solve when it is doing the code generation. It assigns a register for the variable. But here, this particular part is not fixed. A compiler is typically works on a pre-designed hardware. So that all the functional units are allocated, you know how many ALUs are present, whether what is the functionality of the ALU. Here, that's also getting decided, and their compilation has to be done on that particular decided structure. So it is a very flexible type of a compiler. So in terms of this variable storage unit binding, I have to make such decisions, which register it has to go to, or it is go to register, or it has to be assigned to a memory location. All these decisions gets done at the time of variable to storage unit binding. So this is a problem that transfer to interconnect or bus binding. Every transfer that is there. So in this case, what is the transfer? I need to transfer the value R1 from the input of the adder. Not input, output of the adder, because V1 has been bound to R1. So the output of this adder has to come to R1. Output of R2 and R4, they have to go as input to. So these are the transfers that are required. The transfers that are required are the inputs have to be supplied to the adder from the variable V2, wherever the V2 is stored. The V2 is stored in wherever we decided, is stored in R4. So from there, adder input has to come. From adder input also has to come from R2. So these are the transfers, and the result has to be transferred to R1. So I need interconnects for supporting these transfers. I need to have the interconnects. I may have buses, I may have interconnects. Point to point interconnects, or I could have buses. So this is the problem of binding this transfer to interconnect binding. Sometimes there may be multiple buses and you have to choose which bus to use, or there may be an option, or you may be doing the interconnect synthesis and you may be making a decision whether I need to use separate new interconnect, or I can use an existing interconnect. Let me tell you how this interconnect and variable storage unit binding, how are they related. Let us take an ALU. Let us say I have an ALU and I have something else. Let us say I have an adder and I have an ALU. I have one operation which is V1, V2 minus V3 some operation, and somewhere down the line I have another operation V4. V2 and V3 I have put it into some register, let us say R1 and R2. So R1 contains V2, R2 contains V3, and these inputs are going, minus is being performed here, and the register that I am using is R4. R4 contains V1. Let us say V1 has been assigned to R4. Now when I come to this, number of things that I can do. If I bind, let us say if I decide that okay, this particular operation, addition can also be performed in ALU as well as on the adder. I decide to perform the addition over here. I decide to bind, let us say by this time R1 is free, so V5 is stored over here, V6 is stored over here, and V4 is stored over here. If I do that, then I will not need any new interconnects. The only thing I will need is, of course, I need to control the function of this. I need to perform an addition here and I need to perform a subtraction here. But this type of binding, variable to register binding, which is compatible to the variable to register binding that I did at this step, would actually allow me to save the interconnects that are required, the fresh interconnects that are required. Whereas if I don't do this, if I actually bind this addition to here, even though I may bind these registers, I will still require fresh interconnects to get the data into this adder. So what I wanted to show you over here are all these three things are influence each other. The way you bind operation to operators, variable to storage, and transfer to interconnect can have an influence on the total cost of the system. How how many interconnects are you finally require, and so on and so forth. So that is what binding has considerable influence on number of interconnects. And of course, you can also see that scheduling also influences binding, because if there is some other operation, along with this I have scheduled some minus operation, I don't have this flexibility of putting this adder onto the ALU, because subtraction cannot be performed by this unit, only this unit can perform the subtraction. So I have to bind this subtraction over here, and I have no choice but to bind this addition over here. Okay, so you can see that the scheduling also plays. So there is a lot of influence that they exercise over each other, and that makes for the real complexity of this problem. So control and clock synthesis, I talked of the control synthesis already, so let me just go over it quickly. So generate a state machine from the control flow of the algorithm. So given an algorithm is just a sequence of steps, you can break the sequence down into control steps, what is possible to be done in each clock cycle. You can directly draw a state machine. You know how to convert something like a conditional statement into a state machine. It just tests that condition and translates. Any iteration, any type of a loop statement can be again converted into a equivalent state machine. You have to test a condition by which the loop terminates or the loop proceeds, and then that particular condition can perform the branching between going back to an existing state which is part of the loop or going to out of the loop. So one can translate a algorithmic description into a state machine. Of course, we already, when the data path synthesis is done, we had to identify this control and status signals. We synthesize the control part. So the issues in synthesizing the control part is the state assignment, what type of encoding, one hot encoding, minimal encoding. We can choose among that, and then rest of it is Boolean equations. The next state function is nothing but a Boolean equation which can be synthesized using multi-level logic synthesis. Analyze the critical paths to decide on the clock period. So this is the simplest way of deciding the clock period. There are more complex techniques, especially when you want to support multi-cycle operations. Otherwise, the simplest method is just take the critical path and have the clock period larger than that. But as we said before, for more complex designs, one doesn't want to do it. When the variation in terms of the delays for the operators is very large, one may like that a slower operator actually takes multiple clock cycles than just single clock cycle. And all this is done with what is the objectives. The objectives in behavioral synthesis are minimize delay time or maximize performance. So that's a goal that you are working with. Minimize cost or area. So performance may not be an issue cost may be an issue. See, it all depends upon the application. I am designing a calculator chip, let us say. If you take a calculator chip where the inputs are fed manually, a user cannot feed in more than, what is the maximum speed. So, it is going to take hundreds of milliseconds to punch in. You can only type 2, 3, 4 keys in a second. And from the technology point of view, it is very, very slow. You can do a lot of operations in something like 100 milliseconds. Even if you work with 10 megahertz, you can do a lot of operations. So, in this type of an application, performance is not an issue, because the user is going to type in some numbers and then going to see the result, and if the result takes 10 milliseconds or 20 milliseconds or 50 milliseconds, it is immaterial. It should not, of course, go beyond a certain range, but in a certain range it is immaterial. So, in such cases, it is the cost that becomes the design criteria. You want to make the cost of the chip or the area of the chip as small as possible. Whereas there could be situations when you want to maximize performance. Many situations where one would like to maximize performance. Similarly, instead of maximizing or minimizing, having this as an objective function, you can also have objective function that you want to meet certain constraints. The area should not be more than this, or performance should not be less than this. Many of this, for example, anything that you do with speech or anything do with video, there is a fixed frame rate you work. If you, let's say, designing, so now digital TVs are getting designed. If you talk of a digital TV, if only 50 frames are going to come per second, whatever processing you have to do, you have to finish within 20 milliseconds, which corresponds to 50 milliseconds. Here it is a constraint. Here it doesn't matter that if you are able to do it in 5 milliseconds, you don't gain any advantage whatsoever. Because your transmission is only going to be 50 frames per second, there is no point in doing anything faster. So, here it is, in terms of the performance, it is a constraint, and anything below that is acceptable. Okay. So, similarly, in terms of cost, you can have a constraint. You can say that this is the maximum area depending upon what the market is ready to accept, and then you can say that my design should fit into this. So, one can talk in terms of these constraints, and all this synthesis has to be carried out. Imagine automatically, if there is a synthesis that is to be done, it has to also take in these constraints and do the synthesis. It is not just realizing the functionality, but also realizing the functionality. Now, as we talked of before in the last, so the behavioral synthesis itself has been active for around 20 years now. So, the industry has started using it only in the last few years, and still the tools that are commercially available are far from, let's say, I won't just call perfect, but far from, let us say, what they cannot still mimic a very good human designer. Okay. But the problem is, as I mentioned to you before, the very good human designer who has a capability to handle the whole system is very limited. The number of such designers are limited. That's the reason behavioral synthesis is getting pushed into. But on the other hand, in the last 10 years, a lot of new trends are coming up, which also needs to be incorporated, where things are being done manually designed. One is the testability. We had an introduction to testability in this course, where we said that how do we make the designs. First of all, how do we test a design, and also how do we make a design testable. So, one needs to incorporate this testability as part of the design synthesis phase itself. It is not that you design and then you make it testable, but when you are doing a synthesis, can you incorporate this as part of the objective that the design should also be easily testable. So, that is one type of a problem. Second type of thing is power minimization. Trying to make design choices. So, see, the whole game is about exploring a design space, and the reason we are doing it to the tool is the design space is too large, and only a designer with a lot of intuition can quickly home in onto a good design. Otherwise, the design space is so large, and if a designer has to exhaustively search the design space, it is going to be impractical. The design time will not going to be acceptable. So, that is why a tool can search it very quickly. But when the tool is searching such a design space, it is doing to meet certain objectives. The objectives are minimization or meeting the constraints. But along with the objectives on cost and performance, one needs to also have objective on power, whether one could minimize. So, when you are making a choice whether this design is preferable to the other design, you also evaluate in terms of power, which is preferable, which is going to be low power, whether it meets the power constraints or whether it minimizes the power. So, those criteria can also be included. So, today's challenge is to incorporate the behavioral synthesis techniques incorporate these conditions into the behavior synthesis itself. Okay. So that's what people are currently looking at. Okay, so with this we will stop.